Hello everyone, I'm Professor Harrison and welcome back to our module on regression analysis for finance. Today we're going to be covering how to test an individual coefficient and how to build a confidence interval around it. We're following Margot, a graduate student trying to assemble a story her family buried. She's been staring at a negative relationship in her data and she wants to know whether it's real. Were her grandfather's returns actually worse when the rational quant was active trading against them? Or could a slope of that size just be noise? She pulls up another page from her grandfather's records. Last time we built two pieces, a standard error for a coefficient and a t-statistic, which is the coefficient divided by the standard error. Now we're going to use them to actually make a decision. The setup is a hypothesis test, the same framework from the Inference module. For any single coefficient, the standard null hypothesis is that the coefficient is zero. In other words, that this predictor has absolutely no relationship with the outcome once we account for everything else in the model. The alternative is that the coefficient is not zero, and that there's some relationship in one direction or the other. So how do we run this hypothesis test? Well, the good news is we've already actually built out a lot of the math behind what we need. Our test statistic is just the t-statistic that we've already built. We compute it by taking the coefficient and dividing it by its standard error, and this has n minus k minus 1 degrees of freedom. If the true coefficient is really zero, then this statistic will hold a t-distribution centered at zero. So we ask a simple question. How far out in the tail is the value that we actually got? If our t-statistic is all the way out in the tail, a value that far from zero would almost never happen by chance under the null, so we reject the null. If it's close to the middle, then it's the kind of value that you end up seeing all the time, even if the coefficient really is zero, so we fail to reject. We make that precise either with a critical value or a p-value, exactly as we did in inference. Pick a significance level, usually 5%. The p-value is the probability of seeing a t-statistic at least this extreme if the coefficient were truly zero. If the p-value is below your significance level, then you reject. When we reject, we say the coefficient is statistically significant at that level. That phrase just means the estimate is far enough from zero that we don't think we're looking at pure noise. There's a second way to say the same thing, and it's often more useful. Instead of just a yes or no on whether the coefficient is zero, we can build a confidence interval around it. The interval is the coefficient plus or minus a critical t-value times the standard error. For a 95% interval and a decent sample size, that critical value is right around 2. So it's roughly the coefficient, give or take 2 standard errors. And here's the connection that ties the whole video together. The confidence interval and the hypothesis test are the same statement looked at in two different ways. If the 95% confidence interval contains 0, then you fail to reject the null hypothesis that the coefficient is 0 at a 5% level. If the interval doesn't contain 0, then you reject. So a coefficient is significant at 5% exactly when its 95% interval misses 0. That's the duality, and it's the same duality between intervals and tests that we saw back in the module on inference. So let's actually run Margot's test. She regresses her grandfather's monthly excess return on a measure of how active the rational quant has been against him in his book. She wants to know whether that activity has any relationship with his returns. The coefficient on the activity comes out negative. It's about negative 0.6. So in months where the rational quant was more active, the fund's monthly return ended up lower by around 0.6 percentage points per unit of activity. The standard error on that coefficient is 0.15. So let's run the test. The t-statistic is the coefficient over its standard error. Negative 0.6 divided by 0.15, which is negative 4. That's 4 standard errors below 0. With a sample this size, a t-statistic of negative 4 sits far into the tail. The p-value is tiny, well under 1%. So we reject the null hypothesis that the coefficient is 0 at a significance level of 5%. This means that the negative relationship is statistically significant. Now let's build the interval and confirm the duality. The coefficient is negative 0.6 and the standard error is 0.15. Our critical value is about 2, so the 95% confidence interval runs from about negative 0.9 to negative 0.3. Notice that the whole interval sits below 0. It doesn't come anywhere near close to containing 0, which is the same verdict that the test just gave us. The effect is real. It's negative, and a reasonable range for it is somewhere between negative 0.9 and negative 0.3 percentage points per month. So this isn't noise. Her grandfather's returns really were systematically lower in the months where the rational quant was most active against him, by more than half a percentage point a month at the center of that estimate. Margot sits back. The number is real. The rational quant wasn't some incidental counterparty. Their presence in trading against her grandfather was measurably costing him around half a percentage point per month, and the data won't let her explain it away as just a chance. So she stops asking what the rational quant did and starts asking who they really were. She pulls up the rational quant's incorporation papers. The rational quant was registered to a single name, Ruth Sokolova. It's a name Margot has never seen. It isn't in her grandfather's records anywhere, and it isn't signed in a single one of the letters. So she starts her search to find this mysterious person. So that's how we test a single coefficient. We set the null at 0, build the t-statistic by dividing the coefficient by its standard error, and check how far out in the tail it lands. The confidence interval carries the exact same verdict. If it misses 0, the coefficient is significant. If it contains 0, it isn't. This is just the same inference framework from earlier in the course, but now we point it at one regression coefficient at a time.